Today we're going to talk about periodic trends. Now, last lesson we talked about how you can look at the periodic table to determine all the subatomic particles, the protons, neutrons, and electrons. There are also some other cool periodic trends that we didn't really get into. So today we're just going to discuss what we can learn from looking at that periodic table. There is so much that we can learn from the periodic table. We're just going to cover a fraction of it today. But basically the idea is that the periodic table was arranged in such a way that you can look at the periodic table and not have to memorize anything, but just kind of understand how things fit together. And if you can kind of form that understanding and appreciation of the periodic table in a day's lecture, you're doing well. All right, so kind of in review, can you name the 3 subatomic particles of an atom and list their charge? Do you know what that number on the periodic table tells us about the number of protons in an atom or element? If an atom is neutral, how are the number of protons related to the number of electrons in an atom? That's kind of what I expect you to know at the beginning of this lesson. So how can you know protons, neutrons, and electrons from looking at the periodic table? All right, so remember that atomic number that you see up here on the top, Z, that identifies the number of protons an atom has. So if it's neutral, that can also help you figure out the number of electrons an atom has, because remember the atomic number Z is always the number of protons in an atom. If you ever change the atomic number, you change the number of protons and you also changed what element it is. Okay, but if it's neutral, it also changes the number of electrons. But you can change the number of electrons a lot more easily than you can change the number of protons. All right. So that's kind of what I expect you to know before today's lecture. I hope today's just kind of adds to that and gives you more things to think about when looking at the periodic table. So I kind of like this joke. How often do I like jokes about chemistry? Periodically. All right, so these are the periodic trends that we're looking at. All right, so first of all of the periodic table has numbers at the top. So whenever you're looking down and you're going down a column, those are all called groups. They can also be called families. So it's sort of like a family in real life. So I look a lot like my 2 sisters. We have brown eyes, we have brown hair, we look very similar. That's how groups work, families work, is that they share certain properties. Okay, so for instance, group 1 atoms, lithium, sodium, potassium, the family trait that they have is that they react extremely explosively with water. All right, and so that's just kind of a trait they have. It's the same way for every other group, is that if things above it and below it share similar properties. And so it lets you know a little bit about the properties of an element if you know the properties of any other element within the same group. Whereas periods, they're periodic, meaning they transition from left to right. Okay, so there's normally trends that increase, decrease, change in some form or fashion as they go from left to right. And so basically you'll have a periodic trend. So say something increases from lithium all the way to neon, it's going to do the same as it goes from sodium to argon. So it's periodic. Okay, and so those also have numbers. The thing to note about the groups is sometimes you'll see the top written as, instead of seeing 13, whoops, let me go and change to my other pen for you, is instead of seeing 13, you'll see this one just called 3. 14 is going to be 4, 15's 5, 6, 7, and 8. Okay, and basically then these are all intertransition metals, and so typically these don't matter as much as the outer ones do, and so sometimes you'll have it be like 3B, 4B, and so all these inner groups will get a B next to them, and then these are all considered your A's. Okay, but don't worry about that. Just note that depending on what group it's in, you're going to know properties about it. All right, so just kind of to recap, periods are horizontal rows across the periodic table. The trends that exist typically change as you move from left to right. So for instance, atomic size decreases as you move to the right. All right, we will talk a little bit more about that later. Any repeating trend is called a periodicity, and so that's where it gets the name of a period from, is that it repeats in every single row, and so you've got periods. All right, so let's look at this example. So this is the one I just told you, that what happens to atomic size as you go from left to right. All right, so for instance, lithium, beryllium, boron, carbon, nitrogen, oxygen, notice that the dots that are shown here all get smaller as you go from left to right. Okay, also, what happens as you go down a column? It gets bigger. Okay, so it gets bigger as it goes down, and it gets bigger as it goes to the right. So if we were to really talk about the periodic trend that's represented by these atoms, we would talk about how they decrease in a family and increase as they go to the left within a period. Groups and families are vertical columns in the periodic table. They exhibit similar chemical behavior, and so that's what I just talked to you about. Atomic size decreases as you move, and I actually meant to say as you move up within a family. Okay. Often there are traditional names associated with them. So same way as everybody within a family has the same last name, groups or families have traditional names that just kind of help characterize them. All right, so what are those common names? Group 1 is alkali metals. Group 2 is alkaline earth metals. All right, so notice the difference on that. Alkali, so that's like your lithiums, your sodiums, your potassiums. Alkaline earth, those are going to be your second row, your calciums and that kind of thing. Your transition metals is that huge block right there in the middle. Okay, so groups 3 through 12 are all very common, so they're the trickier of them. They within each group they contain a lot of similar properties, but transition metals, if there's ever a break or a change in a periodic trend, it normally happens within the transition metals. And then really 13 through 16 don't really have common names. Some people call group 16 the chalcogens, but I typically don't, so I'm not going to worry about that. But chalcogens, if you're interested in it, that's the name of group 16. Group 17 are called halogens, and group 18 are noble gases. So noble gases, those are typically going to be the ones that you'll see, like the xenon, the neon. They've got full octets, which we'll talk about that later on. But basically, if you just kind of know what these names are, you'll be good to go. So noble gases, halogens, alkaline earth metals, and alkali metals. Okay, so let's look a little bit further at each of these. So, for instance, these are pictures that I kind of referred to earlier of a substance that reacts really strongly with water. So think about it a second, see if you remember which substance I mentioned. That's right, group 1. Group 1 reacts really strongly with water. So if you take a chunk of sodium metal and you throw it into water, it's extremely explosive. Same thing for potassium. All right. So basically, with those metals, they share a similar property. I do suggest going to YouTube and just type in potassium reacting in water and just watch the video. They're pretty neat to watch. All right, so let's do a concept check. The elements copper, silver, and gold are 3 of the few metals that can be found naturally in their elemental state, which means you can actually go and find copper in a mine somewhere. And so that's why they're used in coins and jewelry. It's because they're found naturally, but then also they resist corrosion pretty well, and they're pretty. People like them. So how is the fact that these metals have similar properties reflected in the periodic table? What do you think? Where would you expect to find them on the periodic table? Well, 2 things. First of all, you know they're all metals, copper, silver, and gold. They're all found actually in transition metals, and so that's where the transition metals part of the name comes from, is the fact that they're composed of metals. Okay? And then additionally, they share similar properties. So what does that tell you? That means they all exist in the same family. All right, so if we look at, let's go back to a periodic table. All right, so if we look at gold, so that was gold, silver, and copper, they're all found right here. So all of these are in the same family. So that's why they all have similar properties. The resistance to corrosion, found naturally, they're in the same family. So they're going to share characteristics. All right. So furthermore, I just mentioned that metals, transition metals, are metals, okay? But you can go even further than that. You can look at metals versus nonmetals versus metalloids. So metals are found on the left side of the periodic table. They're shiny, they're malleable, and they're good conductors. Nonmetals are on the right side of the periodic table. They're poor conductors, they're dull, and they're brittle. Whereas metalloids, they're kind of the transition between them. They're right between metals and nonmetals, and sometimes they act more metallic than other times, and other times they act more non-metallic than other times. So they kind of share a little bit of both metal and non-metal properties. So let's kind of look at it. This line right here Okay, this kind of green line on the periodic table. That's where your metalloids are going to be located. On the right-hand side, these are your nonmetals. And over on the left, you've got your metals. And so that's why your intertransition metals are over here, because this line here in the middle is your metalloids. And anything to the right of them is nonmetals, anything to the left of them is metals. And I thought I had a better picture of that. I guess I don't. Okay, but if we kind of look at here, this slide right here, is it blown up? Boron, silicon, germanium, arsenic, antimony, and tellurium, those are your metalloids. And then everything in pink is your nonmetals, and everything in brown are your metals. Okay, so just note, if I ever ask you, and this will be used so many times in this class, if I say which side of the periodic table are the metals located, you have got to say the left side, and know that that line that kind of runs down them, zigzag kind of stair-step pattern, those are your metalloids, and your nonmetals are on the right-hand side. So just drill that into your brain now. Nonmetals are on the right, metals are on the left. Okay, that will be very important throughout pretty much the entire course. Okay, so let's go back to this transition metals. The intertransition metals are a small portion of the transition metals. And basically the idea here is whenever you go and you look at your periodic table and you've got that extra little rows down at the bottom, that's because you have special subsets of them called lanthanides and actinides. So the 6 and 7, those rows are lanthanides and actinides. And note that these rows right here actually get inserted right here and right here. So they're still 6 and 7, there just wasn't room for them in the periodic table. Well, there's room for them, it's just we'd have to make our periodic table really, really long. Okay, so just kind of for sake of room, they took this little chunk subset out and put it down below. Those are called lanthanides and actinides. Okay, now atomic size. That's the first periodic trend. That's one we talked about a little bit earlier. The reason for that is it's the distance. Atomic size is classified as the distance between the outermost electrons and the nucleus. The size of the atom seems to decrease across a period. Now, why do you think that would be? Okay, so let's look at each one. And notice we're only looking at the group A's. Okay, so the 1, 2, 3, 4, we're only looking at group A's here. And so that's where the periodic trend holds very true. So as we go from left to right, what happens to our number of protons? Lithium has how many? 3. Beryllium has 4. Also, if we're looking at the neutral atoms, what happens to your number of electrons? 3, 4. Okay, so the idea here is as you add protons into the mix, it's going to pull those electrons in tighter and tighter and tighter into it. So therefore, the atomic size, the radius, which is the distance between the nucleus and the outermost electron, is going to be diminished. It's going to be pulled in. So as you add protons to it, those protons are just going to increase in the amount of attraction to those outer electrons, and the outer electrons will be pulled in tighter and tighter and tighter. Okay, and that's as you go to the right. But as you go down, why does it get bigger then? Because we're still adding protons. So what makes it different? Okay, so the idea here is now, as you've gone down the periodic table, you're going to enter into what's called a new energy level. And we'll get to that later. But the idea here is now as you go down, you've added, they're all equivalent. Now when you go from lithium, which has our 3 electrons, and then 4, 5, 6, 7, 8, 9, 10, 11. So sodium should have 11 protons and 11 electrons. Now when you go down, once you reach that neon, it's actually going to go back and it's going to increase the size because we're actually going and getting more and more energy. Basically think about it as the fact that the electrons have so much energy now that those protons couldn't hold them in, so they're going to get to the next size up. But then now as you add protons, it's going to decrease more and more. So then as you go from argon to potassium, it increases again, but then it decreases. And then from krypton to rubidium, it increases, but then it's going to decrease. So the periodic trend is that as you go down a column, you're going to increase in size. As you go to the right, atoms are going to decrease in size. Okay? And this is kind of a picture that shows you kind of in a graphic form. All right, so I kind of draw this picture to help myself remember. Everything as it gets closer to the top right-hand corner of the periodic table is going to be smaller. As it's closer to the bottom left-hand side of the periodic table, it's going to be bigger. If you can just write down this graph and kind of use that to help you, I think this will kind of help you keep the trends straight. Okay, so let's practice a little. Which element has a larger atomic size, carbon or oxygen? Another way of saying it is which one's closer to the top right of the periodic table? Oxygen. So since oxygen is closer to the top right-hand side of the periodic table, it's going to be smaller. So that means carbon is larger than oxygen. Okay. What about lithium and potassium? Potassium's closer to the bottom left-hand side of the periodic table, so therefore potassium has the larger atomic size. Okay. Ionization energy. That's the next periodic trend we're going to look at. So ionization energy is the energy required to remove an electron from an atom in the gaseous state. All right, so remember when we talked about all of our different electrons, as we increase from lithium down to neon, for instance, we're adding an electron every single time. So what that means is all of our atoms, they want to have, except for hydrogen and helium, they want to have 8 electrons in the outer shell. So if I draw, for instance, lithium. Lithium has 3 protons and 3 electrons. All right, so if I throw my nucleus here, and then I draw a bunch of rings around the outside, the rule for drawing rings is the inner ring can only hold 2 electrons, and then every additional ring from there on out wants to have 8. So with 3 electrons, I can have 2 in the center ring and 1 in the outer ring. So what that means is that in order to be happy, it can either only have the 2 in the middle or it can have 8 on the outside. So if it loses that electron, then it's going to be happy. Or if it gains 7 electrons, it's going to be really happy. So let me ask the question, which do you think is harder to do? Lose 1 electron or gain 7 electrons? Okay, good. It's easier to lose the 1 electron than it is to gain 7, which means lithium has a high ionization energy because lithium, it doesn't take a lot of energy to remove an electron from the atom. So lithium would have a high ionization energy. Okay. So what if we come over to fluorine? Let's do fluorine next. Fluorine has 9 protons and it has 9 electrons. Okay, so if we draw its nucleus here in the middle, and then 1, 2 little rows around it, put 2 electrons here in the center, and then we've got 2, 3, 4, 5, 6, 7, 8, 9. So I just drew all 9 electrons on this orbital diagram. Okay. All right, so what that means is, let's count. We've got 2 electrons in the center ring, so it's happy. But in our outer shell, our outer ring, how many do we have? 1, 2, 3, 4, 5, 6, 7. So we have 7. So what that means is we need to have 8 electrons in the outer shell to be happy. So for fluorine, what that means is it can either lose 7 electrons or it can gain 1. Which do you think is easier? Lose 7 electrons or gain 1 electron? Okay, what it does is it wants to gain 1 electron because that's easier. So it's not going to lose 7. That's way too hard. So if it's going to want to gain 1 electron, do you think it's going to take a lot of energy to remove electrons? Yeah, it's going to take a lot of energy. Okay, so the idea here is that you're going to have even higher ionization energy for fluorine. Okay, and so the idea here is that it's not going to take nearly as much. I'm sorry, I meant to write low over here, because it's not going to take a lot of energy to remove an electron from lithium, whereas it's going to take a whole bunch of energy to remove an electron from fluorine. So I apologize for being confusing earlier. So it's going to be a high ionization energy for fluorine because it's going to take a lot of energy to remove an atom. Okay, whereas before, lithium wanted to give up that electron, so it doesn't take a lot of energy because it's willing and happy to give up its electron. So kind of the idea here is things on the left-hand side of the periodic table have a low ionization energy. Things on the right-hand side, they start out with more electrons in the outer shell, so it takes a lot more work to remove an electron than it does to just give it an electron. Okay. On a side note, that's also what allows fluorine to become negatively charged and lithium to become positively charged, but we'll talk more about that later. Okay. So, for ionization energy, this is kind of a bar graph that's showing it. So it's really high up in the top right-hand corner, and it's really low in the bottom left. So if I were to represent it with my big stars, ionization energy, it's the opposite of atomic size. So it's the largest in the top right-hand corner. It takes a lot of energy to remove an electron, and it's the smallest in the bottom left-hand corner. Those elements are super happy to give up an electron. It'll be so much more stable if they can just give it to it. So it just gives up those electrons very happily. Okay, so if you'd ask which element has a larger ionization energy, magnesium or phosphorus? Phosphorus would have the larger ionization energy because it's closest to the top right-hand side of the periodic table. Arsenic or antimony? Which one's closest to the top right-hand corner of the periodic table? Arsenic. So arsenic's larger than our antimony. All right, so this was the graph I was actually looking for earlier that shows the metalloids here in blue, the nonmetals on the right-hand side, and the metals on the left-hand side. Notice hydrogen is actually colored green, and that's because it acts as a nonmetal. So that's why sometimes you'll see hydrogen on the right-hand side of the periodic table located next to helium. But technically it's also should be on the left-hand side because it shares traits with lithium, sodium, potassium, etc. And so that's why it fits in really well in group 1. And so it's your kind of one exception to a lot of rules. All right, so the idea here is as stuff is closer to the top right-hand side of the periodic table, it's going to become more non-metallic. As it's closer to the bottom left-hand side of the periodic table, it's going to act more like a metal. So kind of the further it is from non-metals, the more it acts like a metal. So that's what it means by metallic character. Metallic character is the amount an atom acts like a metal. So it's going to be biggest in the bottom left-hand corner of the periodic table. All right, so here's kind of the chart that summarizes that. Nonmetals are in the top right-hand corner. Metallic corner is in the bottom left-hand corner. And that's just because it requires little energy to remove an electron, and that's what causes it to act like a metal, is its ability to lose electrons. All right, so which element has a larger metallic character? Sn or Te? Sn. Sn is larger because it's closer to the bottom left-hand corner. What about silicon or antimony? Or tin, sorry, silicon or tin? Tin, because it's closer to the bottom left-hand corner. So this is kind of what you have to think about whenever you're trying to decide which element has a larger radius, larger ionization energy, larger metallic character, is how is it and where is it located on the periodic table? All right, so kind of to recap all this. Atomic size, largest in the bottom left-hand corner. Metallic character, largest in the bottom left-hand corner. And ionization energy, highest in the top right-hand corner. Okay, so in keeping these straight, just kind of think about what trends you can have, think about what groups are, think about what periods are, and all this character, what you can learn just simply from looking at the periodic table.